Happy Pythagoras Day. I am posting this video on July 25th, 2024, and the numbers 7, 25, and 24 form the sides of a right triangle. This doesn't happen very often. The last day that this happened was on December 16th, 2020. The numbers 12, 16, and 20 also form the sides of a right triangle. Now, what do I mean by this? So here I've got a green mark on the side of the paper, and this green mark is 7 centimeters from the corner. On the other side, I've got another green mark, and this green mark is 24 centimeters from the corner. And if I draw in the hypotenuse of this right triangle and draw this very carefully, if I draw this very carefully, the length of this diagonal line, the hypotenuse here, will be exactly 25 centimeters. So if this is exactly 7 and if that's exactly 24, the diagonal line that I just drew, the hypotenuse, will be exactly 25 centimeters long. Now, how do I know that this is going to be exactly 25 centimeters long? We can show this by some mathematics. So here I have a picture of a right triangle, and I've drawn 4 copies of this right triangle. So let's make this side 7, this side is 24, and this hypotenuse is going to have some length c. It turns out it's going to be 25, but I'm going to show that with this little demonstration. Now, these other triangles have the same dimensions, so 7, 24, and c. Here it's 7, 24, and c, and likewise up here, 7, 24, and c. Now you'll notice that the white figure in the middle looks like it's a square. If I connect these hypotenuses together, it looks like I get a square. Now this turns out to be the case. The reason this happens is because that this angle plus this angle plus this angle must be 180 degrees. The sums of the angles of any triangle work out to be 180 degrees. So if I add these 3 angles up, I get 180. Also, if I look at these 3 angles here, clearly that's half of a full rotation. So that's also has to add up to 180 degrees. So this plus this plus this has to be 180. Well, this is the same triangle as this. So this angle is the same as this angle. So the only way that happens is if this interior angle is also a 90-degree angle. This must also be 90 degrees. This must be 90 degrees. This must be 90 degrees. And since it's the same hypotenuse, we get a perfect square. Now, the way that I will show that, or the way that I will compute the value of c here, is by computing the area of this big square in 2 different ways. First off, we notice that each side has length 7 plus 24. And of course, that's a square. We've got right angles in the corners. And so the area of the big square is going to be 7 plus 24 squared, whatever that is. All right, now I will compute the area of the square in a different way. Another way of computing the area of the square is looking at these 4 green triangles. These 4 green triangles, the area of one of these triangles is going to be 1/2 the base times the height. And so the area of one of the triangles is going to be 1/2 times 7 times 24. And there are 4 of these triangles. So if I multiply 4 times that, that'll be the area of the 4 triangles. Now I'm missing the part in the middle, so I need to add the area of the square in the middle. And of course, the area of the square in the middle is going to be c squared. Okay, now we're going to solve for the value of c. And to do that, we'll just plug into the calculator. So first off, 7 plus 24 squared, that's equal to 961. That's the area of the square. Another way of finding the area of the square is we add up the triangles here. So 4 times 1/2 times 7 times 24. That works out to be 336 plus c squared, where c is the length that I'm trying to figure out. Now let me subtract this over to the other side. 961 minus 336. That's equal to 625. And so c squared is equal to 625. So that c is equal to the square root of 625. And so punching the calculator, the square root of 625 is exactly 25. And so that proves that the hypotenuse of one of these right triangles, or of all these right triangles, is equal to 25. Now, this doesn't happen very often that these sides of a right triangle are all integers. And so there's a few famous ones. So 3, 4, 5 is the smallest such right triangle. The next one up is 5, 12, 13. And then there's 8, 15, 17. And the one we're talking about today, 7, 24, 25. And of course, I could multiply these by some constant. So like if I doubled all of these, I would get 6, 8, and 10. And this would also form the sides of a right triangle. Now, how do we tell that this is the form of a right triangle? Well, I encourage you to repeat the argument that I just did in this video. So let's let one side of this right triangle be A, the other side B, and the hypotenuse equal to C. And kind of label the other sides and then repeat the argument that I just did and solve for what C is. And it turns out that you'll come out with the magic Pythagorean formula, Pythagorean theorem, pardon me, A squared plus B squared is equal to C squared. And it turns out for all of these, 3 squared plus 4 squared is equal to 5 squared, 5 squared plus 12 squared is equal to 13 squared. And it doesn't often work out that you get all integers. Often you get some square root involved. But for the ones that comes out integer, these are special cases called Pythagorean triples. And we want to make note of that. And it's indeed especially rare day that the number 7, 25, and 24 actually correspond to a date on the calendar.